All right, so in Math 676, I would like to talk about the next step after solving a partial differential equation in a dimension-independent way, namely to make this equation a little bit more interesting. So far we've solved a Laplace equation on unit square, and you will frequently hear me talk about the fact that these sort of model problems really, in the long run, don't do mathematics very good. Mathematicians have solved the Laplace equation on the unit square for decades, and there really is nothing new that can be done anymore in this regard. It is actually something that is sort of the running joke in numerical mathematics, that we keep solving the same problem, which is always the Laplace equation on the unit square. So after doing this for the last two tutorial programs, one of the things that we need to do today is to make it a little bit more interesting. So in particular, what we're going to do is we look at a different domain, and well, we modify slightly the Laplace equation. Namely, we're not going to look at minus divergence u equals f anymore, but we're going to look at an equation of the form minus divergence a of x gradient u equals f, where a of x is a spatially variable coefficient. So you can think of this as a model problem where you have a membrane. I told you that the Laplace equation, you can think of this as a membrane, for example, a two-dimensional membrane, where we apply a certain force from below and we push it up. So the right-hand side, F, would be something like the force density that we apply. If we have a coefficient a of x in the Laplace operator, so instead of Laplace we have minus divergence a gradient u, then the coefficient in there would be something like the spatially variable stiffness of this membrane. So where a of x is large, the membrane is very stiff. Where a of x is small, the membrane is rather soft and easy to deform or easy to stretch. So it is something like a spatially variable membrane. And I would like to show you the equation or the solution of this sort of equation. And in particular, I would like to show it to you in a case where we really consider what happens if we make the mesh finer and finer and finer. And in step 5, what we're going to do is we just look at the equation as, we look at the mesh as something that we refine globally. One of the things that we will see when we look at the solution that we get out of this is that it turns out that it's not really necessary to refine the mesh globally. There's absolutely no point in this, but this is something that we will only see when we see the solution. So then without further ado, let us look at step 5. Step 5 is, has a number of small improvements that I mostly will not discuss in much detail. But then, in particular, it shows how to solve on a succession of globally refined meshes, and it will have a non-constant coefficient. So if you go to step 5, then the bottom of it is going to forget about everything that is in comments here. That is something that we discuss in more detail in the documentation of this program. The bottom, the bulk of, or the really important part of step 5 is essentially that we create, out of this template that we wrote in step 4, we create an object of kind step 5 angle brackets 2, we call it Laplace problem 2D, and then we run it. And you could as well run it in 3D if you wanted to, but that's not our goal. So step 5 essentially does the following thing. So it creates at the very beginning the mesh, and it does it not by calling one of the functions in grid generator, although we could do this, but it reads a mesh from a file that's called circlegrid.inp, and it reads it with a class that is called grid_in. That is essentially our way. So this is a class that can read meshes in a variety of different file formats. For example, it can read this INP format, which is defined by a, it's called, INP is the file ending of a file format called UCD for unstructured something data. I forgot, it's been so long. But it is one of the many file formats that we use for meshes. Grid_in has a number of other methods that can read files in other formats, and this pertains to 2D and 3D meshes, small and big, whatever you want. So what we're going to do is we're going to create an object of this kind. We attach to it a triangulation, and then we say from this file, please read the data and put it into this triangulation. Then if you go back to step number 1, so I should explain what's in this. So this file circlegrid.inp, you might already have inferred what it contains. It contains cells that together describe a circle. And if you just refine the cells without telling anything about the boundary, then you get the same effect that we discussed when we talked about step 1, namely that the outer boundary will be a polygon that is described by the coarse mesh, because the triangulation by itself does not know where to put new vertices if you refine the mesh. That means if you replace every cell by 4 children. So what we have to do is we have to attach to it an object that describes the boundary. So this is this object boundary here. It describes a hyperbolic boundary. So in 2D, a hyperbolic boundary would be a circle. And then we attach this to the triangulation for part number 0 of the boundary. As I said there before, the default for all the boundary indicators is 0. So by default, all of the boundary is encompassed by boundary indicator 0. And then we're going to do the following thing. So we do 6 refinement cycles, starting at 0 up to 6. We're going to produce some output at every cycle. And then we do the following. So at the beginning of every cycle, if this is not the first cycle, then we're going to refine the mesh once globally. If this is the first cycle, then we just stick with the mesh that we originally had. So we output some numbers of active cells, and then we essentially call exactly the same set of functions that we had before: setup system, assemble system, solve, and output results. And the only so these are basically one-to-one copies of the previous functions that we had in step 4, for example. The only difference is that in output results, we pass the number of the refinement cycle as an argument, because we want to create graphical output files for every refinement cycle. And so if you look at this, this function here, output results, the name of the output file is going to be solution-cycle.eps. So this is really all there is to the overall structure of the program. The only other thing that I would like you to pay attention to is in the place where we assemble the matrix. So I told you that we want to solve the problem not minus Laplace u equals f, but minus divergence a of x gradient u equals f. So if you put this into the weak form, you multiply from the left with a test function phi, and then you integrate by parts. In that case, your bilinear form, that is the thing that from which you compute your matrix entry, is not integral grad phi I grad phi j, but it is actually integral a of x grad phi I of x dot grad phi j of x. So where we multiply grad phi I and grad phi j, we also have to multiply it by a coefficient. So what we're going to do is in this assemble system function here, we create an object of type coefficient dim. And this class is defined up here. So coefficient dim is derived from a deal.II class that we call function. And it has a member function value, and it has a member function value list. You can read up on this in more detail, but essentially what they do is that, so value, for every point that you pass to it, it returns to you the value of this coefficient. And what we're going to do is so p dot square, so that means that the L2 norm squared of this point, of this 2 or 3-dimensional coordinate point, is less than 0.5 squared. So in other words, if the distance of this point at which we evaluate this function is less than 0.5 from the origin, then we return 20, and otherwise we return 1. So if you go back to the description of what this equation with this variable coefficient meant, that this is a membrane of variable stiffness, then this would be a membrane that is 20 times stiffer on a circle around the origin of radius 1/2 than it is on the outside. So you can think of this maybe as a very thick membrane in the middle and a very thin membrane on the outside. So what we're going to do in Assemble System, we create an object of this kind, okay, and then we're going to create a vector, coefficient values. That's a collection of double values that we call coefficient values, and there are, in this vector, there are as many elements as there are NQ points. Now NQ points is a variable that I have defined here. So I'm asking the quadrature formula, how many quadrature points do you have per cell? So in this particular case, I have used a Q-Gauss 2 formula. So in 2D, this would be a 2 by 2 formula. So in 2D, it would return in this place here, NQ points equals 4. In 3D, it would automatically return 8. So you see the point of this variable here, that I do not want to hard code this sort of behavior. I don't want to have to think about whether it is 4 or 8 quadrature points, or maybe if I increase the polynomial, if I increase the order of this Gauss formula to 3 or to 4 or to 5, I don't want to have to change anything down here. All of these things happen automatically if I ask the quadrature object how many quadrature points it has. So at this point, I have this function that's going to return to me the value of the coefficient, and I have a place where I can store the values of this coefficient at the quadrature points on the current cell. And so what I need to do is that I have here my loop over all the cells, and then at the top of this loop, after setting the local contributions to 0 and reinitializing the FA_values object, I'm going to ask the coefficient object to please give me the values of this coefficient at these locations, namely at the quadrature points that FA_values has computed, and put this into this coefficient values array. So at this point, after this call, I know in coefficient values for every quadrature point what the corresponding value of this coefficient is. And that's of course what I'm going to use when I compute the bilinear form. So the bilinear form is simply going to be the gradient of shape function I at quadrature point Q point times the gradient of shape function J at the same quadrature point times the value of this coefficient at this quadrature point. That's my bilinear form that I get out of integrating by parts. And the right-hand side is again going to be equal to 1. So there's just one other thing that I need to point out. So when you ask FA_values dot get quadrature points, that gives you back an array of all of the quadrature points on the current cell. And I told you when we talked about step 3 that FA_values computes exactly the things that you want, but nothing else. So in step 3, what we wanted is the values of the shape functions for the right-hand side, the gradients of the shape functions for the bilinear form on the left for the matrix, and the JXW values. The quadrature points were not in this list, but here I do need the quadrature points. And so if you look at the top here at the declaration and initialization of this FA_values object, I also add the update values flag here. So I'm sometimes asked, what does it mean here to have this vertical bar? All of these are essentially bit fields. And if you concatenate them, this is a binary OR, then that means that I'm setting the bit in this flag for the values, I'm setting the bit for the gradients, I'm setting the bit for the quadrature points, and I'm setting the bit for the JXW values. Whereas all of the other bits that are returned as the number of this third argument of this constructor, all of the other bits that correspond to second derivatives, to normal vectors, and so on and so forth, they remain unset. So I'm telling the FA_values object that to please also compute the update quadrature points. If I didn't do this, I would get an error message, and I can show you later how this looks. But so this is essentially what we do in this program. And so now let me show you what happens when I run this. So as always, I call cmake, which initializes the make system. Then I call make. I already did this before. I can run make run. And so it's going to run 6 cycles of finer and finer and finer meshes. So it starts out with 20 cells. This is what it read from the input file. Then it refines it once. In the next cycle, that gives me 80 cells. Then it gives me 320 cells. Every time, every cell is divided into 4. And what I get out of this is files solution 0 to solution 5.eps. So I'm saving this in EPS format now. And I can use, again, Arcular to look at this. Solution 0.eps, for example. So my solution looks like this. I should make this a little bit smaller. So this is a little bit hard to see, but what you should take away from this is a circular domain where I have a few cells on the outside and then a few cells on the inside. And so if I refine this, then I get this particular solution here. Right? That already looks more like what I want. And if I keep doing this, let's say for the 4th iteration, I have something of this kind. Okay, and the 5th iteration looks like this. So when you look at this, you will find quickly that EPS is probably not the best format for this. In particular, there's nothing interactive that I can do with it. It just outputs the solution as it sees it. But I can't, for example, rotate it. I can't look at it in a different color bar. This program essentially just wants to demonstrate that we can use many different output formats. You can, of course, change this. So if I go to, and open the actual file, so where we say write EPS, I could, of course, say again write VTK, and then let me adjust the file name again to .vtk. No, and I say make run. Then it's going to output all of these files as .vtk files, with which I can work exactly the same way as before. So I don't need to go into much more detail. You've seen how to do this, so if I look at the files, there are now .vtk files for each one of these cycles. The thing that I wanted to show you is what happens if you would have forgotten to tell the FA values that you actually want to access these quadrature point information. So if I look again at the source code, I should strip the comments out of this again. So it's going to look like this. This is a lot more readable for me now. So if you go back to the place where I declare the FA values object here, and let's say I had forgotten this and I had done it exactly like I did in step 3 and step 4, for example. So let me remove this one here. And let's see what happens when I first compile this. So from a syntactic viewpoint, this is of course entirely correct. The compiler is not going to complain about it. But semantically, the program is not correct because it tries to access data that hasn't been computed. So if I run this, what I get is something like this. So it gives me an error message that says, in this function, deal.II : FA value space get quadrature points. Okay, so we already identified where the problem is. It says that this condition is not satisfied here. Okay, so it says that the updates flags do not include the update quadrature points value. And it says access to uninitialized field. So you have to sort of know what this means, but it already gives you sort of an indication of, you know where it happens, namely in get quadrature points. You know where it was called from assemble system. Assemble system was called from run. Run was called from main. So you know exactly where it happened, and you probably at this point again you have a good idea of what's going on. Of course, if we had set this up in Eclipse, for example, one of the things that you would do is you would just run it in the debugger, and you would actually get to see where did the debugger stop. Where is the place? What is the exact condition that is being tested? You can look at the values of variables and so on and so forth. So I don't want to show you this again here. We looked at this at one of the earlier lectures, but it's very helpful to know how to use a debugger, how to go through these sort of things. So with this, I will end this class on step 5. The thing to take away with, let me at the very end show you the solution once more, the solution on the finest mesh. So if I look at the solution on the finest mesh on this would be solution5.vtk. If I add the solution and I elevate it with transforms elevate, so I get a solution that looks like this. Actually, so it opened the entire database, but I can zoom through the individual levels. So this is from solution, you see this up here, solution, so I start at solution 0, 1, 2, 3, 4, 5. This is not particularly well elevated. Let me show you how this looks. Transform elevate, elevation relative to the solution value. So if you look at this solution once more, you will find that it looks a little bit like we expected it to be. We said that it's a very stiff material on the inside and a very soft material on the outside. And so the inner disk with radius 1/2 is going to be very rigid, whereas the outer part of it deforms easily. So what you get from a material like this, or from a body like this that has two different materials glued together, is that you typically get a kink in the solution. And for those of you who have a little bit of a background in the finite element method, you will understand, of course, that the quality of approximation of your numerical solution, so how close the numerical solution is to the exact solution, the quality of this approximation depends a lot on how smooth the solution is at one particular point. So over here, for example, the solution is very nice and smooth, and here it is very nice and smooth, but it's got a kink here. And so the error in your approximation is going to be localized around this edge here. If you cannot resolve this edge well, you cannot expect the solution to be accurate anywhere. And so one of the things that we will look at in step 6 is to solve exactly the same problem again, but where we do not just want to refine the mesh globally, but where we want to refine the mesh really only where it's necessary. And only where it's necessary in this particular case means primarily around this edge. And so that means that we have to use a mesh that is adaptively refined, that becomes finer and finer and finer around the perimeter of this interface, whereas it can remain essentially as coarse as it wants on the inside of this disk and maybe around here as well. So what that will lead to is adaptive meshes and all of the, let's say, slight complications that come with it, and that's the purpose of step 6. Okay, so with this, that terminates the class for today, and we'll come back to step 6 the next time.